students, welcome to the 7th session of our first module in Mechanics of Solids. The students, today we are going to learn a topic called plane state of stress, right? Plane state of stress. Plane state of both stress and strain. First we will study plane state of stress. Okay, so students, you know how to write the state of a stress in Cartesian, in metric form, right? Sigma xx tau xy tau xz tau yx sigma yy tau yz tau xz tau zy sigma zz. So this is a general form of a state of stress in Cartesian form or in the three-dimensional form. So students, now we are going to learn the plane state of stress. So we are considering a particular plane only. So if we are considering only xy plane, so if in a given state of stress, there may exist a coordinate system such that for this system the value of all these terms of stress becomes zero. All this will become zero. So such a state of stress is called plane state of stress. So here tau xz or tau zx and tau yz and tau zy and sigma zz are zero. So whenever the value of sigma z equal to 0 or sigma zz equal to 0, tau xz or both are same, right? Both are same. So both this value are 0. Similarly, tau yz or tau zy equal to 0. So such state of stress is called plane state of stress. Plane state of stress. So students, here we have value for the stress, whether it is normal stress or shear stress. The value is present only in xy plane. So this state is also generally known as two-dimensional stress, 2D. So previously we have considered three-dimensional stress. So when this two-dimensional stress is a special case of three-dimensional stress where all these three values become zero. So I will show you. So all the terms with which I have said in its subscript will be zero. So we have stress only in xy plane. So that is why we are calling it as two-dimensional or plane stress. We have only in xy plane. The value for stress is only in xy planes. All other values in z direction are zero, whether it is normal stress or shear stress. Now such condition is called plane state of stress. So I will show you in a figure. Right? This is. So here, so this is y, x, z direction. Okay, so here we have sigma x is there. Okay, sigma x in this direction, sigma y is there. Okay, so in xy plane tau xy is there. Similarly on the other side also tau xy or tau xy is there. Similarly in this direction. That actually that is, this is again tau yx, and this is tau yx. Okay, so this is the state of stress we are considering here. No value for sigma z. So here no sigma z equals 0. Similarly, there is no value for shear stress in zy plane. Uh, so I will show it in 2D form itself. So this is our state of stress. Sigma x is there, sigma xx is there, sigma y is there. So here I am considering tensile stress. Okay, it can be tensile or compressive. Compressive means opposite direction. Now, so this shear stress tau xy in xy plane, in x plane in y direction. Okay. Similarly, this is in y plane in x direction. So this is the state of stress shown in figure. Shown in figure. So you can write this in tensor form. Plane state of stress in tensor form. Tensor form of stress. How? You can write it as sigma x tau xy. Again here tau xy or tau x, both are same due to equality of shear, sigma y. So this is the method to write the plane state of stress in stress tensor form. Okay, stress tensor form. Suppose you are asked to find the components of a stress in a particular plane, an unknown plane with, I will show you in the figure. So here we have the stress here, plane state of stress. I am using another color. Okay. So suppose there is an oblique plane, with some with a normal, n, which makes an angle theta with x direction. So n is the normal. So nx is x component. Direction of cosines are nx is cos theta, because this is theta. Ny will be what? Sin theta, right? There won't be any direction of cosine in z direction. Why? Because this is present in xy plane. So there won't be any nz. So nz is 0. Direction of cosine in. So how to find the state of stress or the stress component in that particular plane for the same particular point? How can you do that? So you have to apply the Cauchy's equation, the same method, the same way we have done in the case of three-dimensional equation, right? So you remember the Cauchy's, right? How to write Cauchy's here? The Cauchy's, suppose we have to find the t vector in n with the ns direction, n as the normal to that particular plane. So tx can be the x component of t in that plane can be obtained using what? nx sigma x plus ny sigma y plus nz sigma z. Since nz and sigma z are 0, that terms is gone. So nx will be what? Cos theta. So sigma x cos theta plus sigma y sin theta. Similarly, t vectors in n direction in y component of that will be what will be the sorry, here a mistake. Actually this is wrong. I will how to write Tx? Tx is nothing but not this way. I'll show you. Tx is actually nx into sigma x plus ny into tau xy, right? Plus nz into tau xz. So this is the method to write. This is the Cauchy's equation. Ty is nothing but nx into tau xy plus ny into sigma y, right? Ny into sigma y plus tau yz into nz. Tau z equal to nx sigma, sorry, tau zx plus ny tau zy plus nz sigma z, right? So in this case, actually all these terms will be cancelled because tau xz, tau yz, sigma z are 0, and these terms will also get cancelled. Only remaining is this one and this one, right? So I will write Txn will be sigma x nx plus tau xy ny. Similarly, Tyn equal to tau xy nx plus sigma y ny, right? So what is the value of nx? Cos theta, ny sin theta. So instead of nx equal to cos theta, ny equal to sin theta. So I am substituting this value. You will get Txn equal to sigma x cos theta, sigma x cos theta plus tau xy sin theta, and Tyn equal to sigma y sin theta plus tau xy cos theta. So this is how you write a component. So if you have to find the net, the t vector, actual t vector in in the plane with n as the normal, you just need to find the square of both the component. Txn square plus ty n square, the root of this value. Okay. Right. So the magnitude, you will get the magnitude if you use the root of both root of the sum of the square of the both the components. Similarly, t vector square is equal to sigma square plus tau square, where sigma is the, what is sigma? Sigma is nothing but in this plane sigma will be the component of the normal stress, the component of t vector in direction of normal. So this will be sigma and this will be tau. Tau will be parallel to that oblique plane, sigma will be perpendicular to that oblique plane. So what is tx? Txy is not, tx will be in x direction, ty will be y direction. Sigma will be perpendicular to the plane. Tau will be parallel to that plane. So that's how we calculate components in a particular oblique plane. So suppose if you know the theta, you know the angle that the normal of that plane it makes with the x direction, you can calculate the components of stress in that particular plane. That's the idea on how to find the stress in a particular oblique plane in a plane state of stress. Okay. Similarly, you can also have a plane state of strain. plane state of strain. Plane state of strain. So there exists in a given state of strain, there exists a coordinate system such that for that particular system you can write epsilon z equal to 0, gamma x z equal to 0, or gamma is zx, and gamma y z is also equal to 0. So if all these three different terms vanishes from that particular state of stress based on a particular coordinate system, that particular state is said to have a plane state of strain parallel to xy plane. xy plane. Okay, parallel to xy plane. So the non-vanishing strain components will be, what all will be the non-vanishing? There will be values for sigma x epsilon x will have a value, epsilon y will have a value, gamma xy will have a value. So you can write the strain tensor, plane state of strain, the tensor for plane state of strain as sigma epsilon x gamma xy or gamma yx and epsilon y. So this is the strain tensor for plane state of strain. Okay, the same method, and you know how to calculate a sigma epsilon x and all, right? How to calculate dou x by dou ux by dou x, and sigma epsilon y dou uy by dou y, right? And gamma xy is nothing but dou ux by dou y plus dou by dou x of uy, right? So where ux and uy are the displacement components, displacement equation, right? So that's it. That's how you write plane state of stress and plane state of strain. Now we will move to an important method or concept called Mohr's circle. Very important. So this is the graphical method. Graphical method to find principal stresses, principal stress and plane, or plane, principal stress or principal plane, and any plane, coordinate stress at any plane with in case. So here we are trying 2D method, Mohr circle 2D. Okay, Mohr circle in 2D. So for 2D case only. So I will show you how. Suppose we are given a stress component, okay, plane stress component as some sigma x, tau x, y, tau x or tau x, y, sigma y is given, right? We are given with this stress state of stress. So how to draw a Mohr circle? So in order to draw Mohr circle, we have to take a coordinate system where this is x. Next we mark sigma, in y we mark shear stress. X direction sigma, y dash. So this is our original point or origin. Okay, students, now we have to so you require scale protractor and all. Okay, so this is a graphical method. So if you draw it in correct way, you can get the value of principal stress and principal plane, direction of principal plane and all. So you take this particular coordinate system, 2D system, where in x direction we mark normal stress, in y direction we mark shear stress. Suppose we have this sigma x and sigma y. Suppose sigma x, you mark sigma x Suppose sigma x is given as some 100 megapascal or 100 kilopascal. 100 kilopascal. So while you are drawing this 100 kilopascal in your in your coordinate system, you have to scale it. Suppose 1 or 10 millimeter equal to some. Oh, so okay, 1 centimeter is equal to some 10 kilopascal. Then 100 kilopascal will be 10 centimeter, right? So to mark 100 kilopascal, you take you scale it. You have to scale down it to some centimeters. So here I will scale 100 kilopascal 10 centimeters. So mark here first sigma x. So what will be this length? This length will be equal to sigma x, right? Okay. Let this point be a. A marked a. Okay. Sorry, to center. Just draw it in center. O A and B, another point B. So from center, so this distance will be sigma x and this will be sigma y. Okay. And suppose the value of tau xy will be some you have got some value for tau xy 50 kilopascal or something. Okay, so you have to mark tau xy in here. Tau xy is in y direction, right? So you just mark tau xy with some point here. One in upward direction, one is positive, one is negative. Both will be same. Actually we are marking the two states, two system, right? Suppose in this figure you can see sigma x and tau x. Suppose in x direction one is sigma x and one is this system, this shear. So actually this shear is actually in clockwise direction, actually clockwise rotation, right? So this system, this couple is trying to deform it in clockwise direction. So this tau is taken as positive, and in y direction another same tau xy a couple is there. It is trying to rotate in anti-clockwise direction. So take anti-clockwise as positive and clockwise as negative. The value will be same, but the sign will be different. So in y direction you have tau xy in positive, and in anti-clockwise, and also in x direction there is a negative, right? So students, you do one thing. So in case of sigma x, you draw negative tau. So this is negative, and in case of y, sigma y, you draw positive. So students, now you have to join this. Okay, you have to join this. So you have to join this. Okay, so suppose this point C will definitely bisect AB. Okay, now with the C as center, and suppose you mark this ABC PQ. Okay, C as center and PC as radius. You you draw one circle. So this circle is known as Mohr circle. So what you have to do? You have to mark sigma x here. This is tau xy, and this will be same tau xy. Okay. So you have to mark this A. A is nothing but sigma x. B is nothing but sigma y. And from B you have to mark tau xy in upward direction. From A you have to mark tau xy in negative direction. Okay. Now you have to join P and Q, and it bisects AB, the lines x-axis at C, with C as center and PCS or PC or CQS or radius. You draw a circle, and that particular circle is known as Mohr circle. Okay. So students, now do one thing. So this is your origin. So students, if you mark this particular point where the circle meets x-axis and this particular point where circle meets x-axis, 2 points you will get. So suppose this is some R and this is S. So students, this particular value of sigma is nothing, mark it as sigma 1, and this particular value of sigma as sigma 2, OS and OR. OR equal to sigma 1, OS equal to sigma 2, and these two particular values are nothing but principal stress. So this sigma 1 is the maximum possible value, sigma minimum is maximum possible, minimum possible normal stress. So students, this particular, or if you calculate this angle, suppose this, you have to take this angle as 2 theta. Okay, 2 theta. You have to take this angle as 2 theta. So if you calculate this angle 2 theta, that 2 theta, the half of that 2 theta, that is theta, will give the direction of principal stress. The principal plane. So in order to calculate principal plane, calculate the angle of principal plane, half of 2 theta, that is theta. So students, if this angle is some 60 degree, then the value of principal plane, the angle of principal plane from the current state of stress is half of 60, that is 30 degree. So you will understand things when you do problems. Okay, so we will do problem in coming session. So this is how you calculate, you find principal stress or principal strain, principal stress and principal plane. Okay, students, I will show another application of Mohr circle. So suppose we are given some 50, 25, 25, 60. So this is our plane state of stress. Okay, plane state of stress. Suppose this means that this will be both the sigma x and sigma y are positive. Okay, suppose there may be cases where either sigma x or sigma y or both can be negative. That means positive means tensile stress. Okay, positive sigma is tensile, negative sigma is compressive. So that is the idea. Okay, So I will do some problem, then it will be more understood. Okay, you don't worry about science now. Now I will show you another application of, suppose application of Mohr circle. Suppose this is our state of stress, and this is our uh, s- coordinate system tau here sigma x. So our two points are one is 50 25, another is 60 minus 25, because if this is positive, this means negative. That depends upon, suppose I kept this as positive and this as negative, because if this is our shear stress, if this is our component, if this is 50 means this is 60, right? Suppose corresponding to, if the, in y direction, if it is clockwise, in x direction it should be anti-clockwise, then only it will remain in equilibrium. Okay, so anti-clockwise as positive and clockwise as negative. Clockwise as negative. Okay, that don't worry, you just you have 2 point, one is 60, one is 50, right? Corresponding to 60, you keep, so this is our point, minus 60 to minus 25, this point, 50 25, this point. So this is 25, this is 25. Okay, so you got 2 points, you join it, you get the center, right? With the center, with this as center, and if this is P and this is P and this is Q, you have to draw a circle. That circle will be your Mohr circle, right? Your Mohr circle. Suppose I am rubbing all these things. So you got your Mohr circle. You got your Mohr circle. Now, so this is the state of PQ. So students, this PQ determines, or PQ shows the state of stress or the plane of stress for the current state of stress, and this particular direction, and this, if this 2 theta gives, this 2 theta gives the plane, principal plane. So this is principal plane, this is current plane of our state of stress. So this angle, half of this angle gives the principal plane, the original value of principal plane. Okay. Now suppose I'm asked to find a stress on a particular plane with the theta from current state of plane. A particular oblique plane with, suppose this is my state of stress. Okay, here, this kind of stress is acting. I'm asked to find a, a stress on a particular plane theta. Okay, theta from maybe, okay, theta from, so students, this is our state of stress, plane state of stress. Suppose you are asked to find value of stress in this particular plane theta from x direction. So this is x direction. From x direction, theta in anti-clockwise direction. If you turn the plane from x direction in anti-clockwise direction with the theta as an angle, you have to find tau here and sigma here. So in order to do that, you just do one thing. So this is our Mohr circle for that particular state of stress. You do one thing, if theta is the angle, you rotate this. Suppose let this be beta. You don't confuse it with the principal plane value. Suppose this is beta. You just rotate this plane and mark a point R such that this angle is 2 beta. Okay, 2 beta. Then students, you get this particular value of tau will be our value of shear stress in that particular plane, and this particular value of sigma will give you sigma for sigma in the plane with the beta as angle. So this is tau beta and sigma beta, and if you need the resultant, you just do one thing. What you have to do? You have to calculate tau beta square. So this is, since this is tau beta, right? This is sigma beta. You just calculate this value. You just measure this value. So this value will give, this OR will give the resultant state of stress. And this angle phi, will give you the value, the direction of the resultant state of stress in that particular plane with the beta as. So suppose this is sigma, this is tau, and your resultant t is acting in this direction. This angle will be phi. This phi can be obtained from here, right? So that is the idea of, phi is from phi is from x direction. This phi will give you the direction of t, the resultant vector from x direction. So students, you one more point. Suppose students, from this point C, from the center of the circle, if you draw a vertical line and mark this, this will be tau max. This will be the maximum possible shear stress. The value will be same, but here it will be negative, here it will be positive. So this particular plane will give you maximum possible shear stress. Actually, this the plane which give you maximum possible shear stress is actually 90 degree from the principal plane. So there is the angle between the plane which give you maximum possible normal stress and the plane which give you maximum possible shear stress is 90 degree apart. Okay, 90 degree apart. So these are the so things will be more clear to you when you do some problems, and in the next session we can do problem. So for the time being, I will stop this session. I hope you have understood how to draw the Mohr circle. That is very important. You should be able to draw the Mohr circle by scaling the stress to the suitable scale, and you should use your protractor or whatever items required for getting the correct geometry. So if you draw with enough accuracy, you will get values or the answer solutions with good accuracy. So that's it.